This is an HEC-RAS sediment user manual video, and in this video we're going to show you how to add sediment to a tributary with a lateral flow series, boundary condition, and a rating curve. So the model that we're working with here is a very simple model. It's got 5 cross-sections, constant slope, constant flow of 2000 CFS. We're going to run it for 24 hours, a downstream stage boundary condition, and the sediment model has a maximum depth, the movable bed limits are in the station, and the bed gradation is all coarse sand. We are bringing in an equilibrium load boundary condition upstream, not because you should use equilibrium load. You should use this with extreme caution. We do not recommend it, but it will help us visualize the result because it will result in a stable bed. So I'm going to run this model without the tributary. And if we look at it, we can look at the flow. This is the generalized plotter in RAS, and each of the quasi and steady flows is actually a steady flow profile in RAS, so you can go look at it, and we can look at the flow. You can see the flow is constant throughout, it's 2000 CFS. And then if we go look at the sediment, we're going to turn on profile, and I ran it for 24 hours, so the cumulative should give us a 24-hour result. And if we look at invert change, there is very little invert change. There's very little bed change. It's an equilibrium model, so it should just be moving through. There's a little bit of rounding error at the boundary condition, but there's no invert change. And if you look at the cumulative mass bed change, it's trivial for this run. Okay, so what we're going to do next is we're going to add a lateral flow to our quasi-unsteady flow boundary condition. Let's save it as, and call it trib. And then we're going to add a boundary condition location. It'll ask us, hey, where do you want this trib? Let's put it right in the middle. And so we're going to come in here, and you'll see this is an upstream boundary condition, so we can't just put in a flow series. It's not a downstream boundary condition, but we could put in a lateral flow, a uniform lateral, and an internal stage. We'll talk about those other ones another time. But let's define a lateral flow. And we'll just 24 hours, 1 hour computation increment. And let's just bring in 10%, a 200 flow, and we can double that just to have coverage. Okay, file save. And so then, if we run our tributary flow in the model, and we go look at the flow, you can see that the flow increases, and it increases downstream of the cross-section you specified it at. This is a feature of both the unsteady and the quasi-unsteady flow model, that when you bring flow into the model, it actually comes in between the control volumes, which means it shows up at the next cross-section downstream. Here's a little schematic that shows that. In this case, we've got the flow coming in upstream and the flow coming in at 500. So what that's going to look like is the flow and actually the load are going to come in downstream of that cross-section in quasi-unsteady and unsteady, which gives us the flow profile that we see here, that it's 2000 and then it jumps up after the cross-section. And this is kind of an important point because steady flow actually does the opposite, and previous versions of quasi-unsteady actually did the opposite, where if you define the flow at a cross-section, the flow comes in upstream of the cross-section, so it shows up at that cross-section. But that's not how the sediment model works. The sediment model works with unsteady and quasi-unsteady, so the flow will come in downstream of the cross-section and show up at the next one. So if you want to bring in a tributary, you should bring in the tributary to the cross-section upstream of where the tributary actually comes into the system. So back to our model, if we go look at our sediment output, and we look at the cumulative mass bed change in profile at the final cross-section, what you'll see here now is that actually there's non-trivial erosion at that cross-section downstream of where we brought the flow in, because we've brought the flow in without bringing any sediment. So we've increased the capacity over this equilibrium state, but we haven't given it any sediment to fulfill that capacity, and so it erodes downstream of a tributary. This is actually something that happens in the real world and something that happens numerically. It's a common numerical artifact. Because sediment transport functions are nonlinear, if you add two flows that are both in equilibrium with the sediment that's coming in, the capacity will increase more than the sum of the flows. And so in the approach that we use to compute sediment transport, two flows that come together in equilibrium will actually form a scour hole. But in this case, it isn't in equilibrium. We actually have sediment coming in from the tributary. And so what we're going to do is we're going to go to our sediment file, and we're going to add a boundary condition. And so just like what we did with the quasi-steady flow file, we'll say add sediment boundary locations, and we'll say, yeah, I want 500. And so now we get a sediment boundary location, and you'll see if we click on this, now we have a couple of options. We can do clear water, which is new. We can bring in a sediment load series. You can actually bring in a sediment load series at any cross-section because you don't need a flow. But you can only bring rating curves in at cross-sections where you have flows because you need a flow for the rating curve. If we were to say go in and add a sediment boundary location at 250, and then click on that, you'll see the rating curve disappears because you can't add a rating curve to a cross-section that doesn't have a flow. All right, let's delete that. And so when we come here, we'll add our rating curve. I have a contrived rating curve here, and this whole example is contrived incidentally and should not be used for project or research purposes. And we're going to just keep it all 100% coarse sand. And you can see for the flow of 200 coming in, we've got a load of 200 tons per day coming in. Say OK. All right, file save. And so now we have a rating curve associated with that tributary. Now if we go in and run, we can go look at our sediment output. And what's happened to the mass bed change, the cumulative mass bed change, which is the total amount of mass that is either added to or removed from the control volume in time. And you can see that actually we've got the opposite effect. You can see that we're in equilibrium right up until the point where we define the tributary, and then the tributary flow and load come into the model downstream of the cross-section. And so we actually have more sediment than the capacity can fulfill. And so we end up depositing downstream of the tributary, and most of it deposits there. So by the time we get to the downstream cross-section, it's equilibrated. And so if we look at the flux, we can look at, say, the sediment concentration, and you can see that the concentration hovers around 40 until you get to the tributary. The tributary comes in between the cross sections and jumps up to the mid-50s, and then it deposits some sediments, so it drops a little bit. And if we actually look at the, that's the concentration, we actually look at the sediment flux, which here we're looking at the cumulative mass to leave the control volume over the whole simulation, which is 1 day of flux in our simulation. And so I don't really love this color, so let me go change that color. Let's get a darker color, and I'll make it thicker. And what you can see is that we've got this equilibrium load coming in that just gets transferred downstream because it's an equilibrium slope. It's at the same slope, and it's a uniform flow condition. But then here you can see that the load coming in at this point is 218.37 tons over the course of the whole simulation. And if you look at what's the load here, it's 330 tons. And so that is the increase in the sediment that's being added to the system minus whatever is deposited. All right, so that is how you add a tributary with a sediment load to an AGC-RAS sediment model with a lateral flow boundary condition and a rating curve. Of course, there are other ways to do it. You can do it with a junction and actually bring the sediment in. If you can avoid that, you probably want to, because of some of the issues with the nonlinearity of the combination of flows and loads I was talking about earlier. Junctions can be a little unstable. So if you can bring in a tributary flow and load with a lateral series, that's preferable. But of course, you can just build a dendritic system in 1D Res as well. My name is Stanford Gibson. I'm the Sediment Transport Specialist at HEC.